Hey programmers, Alvin here. Welcome back to day 17 of the Advent of Code. I think this time around we'll switch things up and we'll jump right into the code implementation. And day 17 is very similar to a previous day of the Advent. It's very similar in that we have some grid and we have some rules for flipping the state of positions of this grid based on the neighbors, right? And right now what I want to do is interpret my input file as sort of just a slice of a three-dimensional space. So let's just start by parsing things up. What I want to do is definitely understand the positions of all of my active spots, right? So that would be all the hashtags here. So let's just start parsing this up. So if I just read the lines of that file, that should give me my initial lines. So let me save that. We'll see what that looks like so far. In part one, we're interpreting this data as if it's just a slice of a 3D state, right? So we have to keep that in mind. So we'll run part one. So that looks good. Let me start by grabbing all of the active, like nodes we'll call them, from this initial state. So I'll create a function, I think. I'll call it const. I'll say get active nodes. And I'll take in, we'll say, our different lines. So for me, what I want to do is really give back, let's say, the coordinates or the XYZ coordinates of every active node in this starting state, right? So let me just iterate through these lines. So I'll just go for, let's say, let x equals 0, and then x is less than lines.length. And along with that, x plus equals 1. And the way I'm interpreting this initial input is maybe this very first coordinate over here, that's going to be 0, 0, right? And then if I went to the right, that would be 0, 1, and so on. So x will give me like the vertical position of this flat surface, and then y will give me the horizontal position of this flat surface, right? So let me just go ahead and iterate through those positions. Nice. And what I have to watch out for here is, it could be the case that maybe we don't have like a square space to begin with. So maybe I'll make sure that I iterate over the respective dimensions, right? Cool. And so at this point, let me actually reference the information or the symbol at that position. So for me, as simple as lines, square bracket, x, y, right? So that should give me the character. So I'll say const char equals that. Then from here, I want to check if it's active, right? It looks like right now hashes or the hashtags represent my active positions or my active nodes. So quite simply, if my char is equal to a hashtag, then it's considered active, right? So what I want to do is store some information. I want the coordinates. So I'll create maybe a nice collection here. We'll call it const nodes. This will be specifically just the active nodes. Something that is pretty interesting about this problem is they say that our space or total like playable area goes infinitely in any or in every direction, right? And it's even a 3D space, so it goes infinitely in all three directions. So the way you actually want to tackle this one is probably to just track the active nodes, right? Because there's no possible way to represent all of the inactive nodes because there's an infinite number of them, right? So we'll just keep track of our active nodes. So whenever I have a hashtag over here, what I want to do is add that node's coordinate into this set. So I kind of foresee me using a few different methods here. I'll create a quick helper function. We'll call it const. We'll say get node from array. So because in the context of my JavaScript sets, I'm going to need some like nice compatible data to store as elements of that set or elements of like an object. And I think a good fit here is like string data. So I'm going to assume that for this helper function, I give it, 3 coordinates in an array. So I'll call this array. And I'll just convert those into an actual string, right? So I can say array.join. I'm going to join on a comma. And I think that will actually be good to go. So it's a pretty small method, but I'm probably going to use it in a lot of different places. What I'm saying is if I called get node from array, and I passed in some coordinates. Let's say the x coordinate was 3, the y coordinate was 10, and the z coordinate was 2, right? Let's see what that gives back. Should just be a nice string. Just want to have a nice clean method name to invoke every time. So let's just see what that gives back. Cool, so I'll just be using these types of strings to represent my nodes, right? And it should be like an ordered triplet, right? So it's always x followed by y followed by z in my scenario, right? So I'll go ahead and create a string for this particular character I just found. So for me, that should be get node from array. So I'll invoke this method and give it those coordinates, so x, y, and they tell us in the prompt that your input is just a flat surface, so we can assume that these all lie in the same, z-plane. So I will just initialize all these to z equals 0 over here, just like this. Cool. And I'll get this as a node. So nodes in my sort of framing right now would be just strings, right? That represent some coordinate, some three-dimensional coordinate. And then from here I can say nodes.add, add that node into my set, right? And then from here, it should be as simple as returning that set of nodes. So let's see how this looks so far. So I'm just going to run get active nodes up here. So we'll say const initial nodes equals get active nodes of the lines. So I should be able to print all of these out. Let's console.log my initial nodes. Run that again. Cool. So I do have a lot of initial nodes here. Let's make sure that these are correct. So 0, 1, 2, good. And then the next one should be 5. All right, 3, 4, 5, awesome. And then the very last one should be almost at the bottom right corner. Cool, looks like this grid is 7 by 7. So this is looking really good. Notice that they all have the same z coordinate. Awesome. So now that I have these initial nodes, we're going to have to also, create some, structure, some scaffolding to quickly find all of the neighbors of a given node. So let's work that into the mix. So really just some helper functions once again. I wish I had a function. I'll call it const. I'll say get neighbors. So I wish, given some coordinate or some point, I want to get all of the neighbors, right? So I'm going to assume over here that I have some, we'll say, maybe node string, or it could be node array. Maybe I'll just take it as an array. And what I'll do is compute all of the neighbors. And they even tell us in the prompt that because you have this like three-dimensional space, you're going to have from any given node 26 neighbors, which is pretty wild because we can also have neighbors in like the diagonal-ish directions, right? So we have to do some computation for that. So we know that when it comes to the neighbors of some node, they can basically differ by at most one coordinate. So what I'll do is I'll pluck out of my array. I'll assume it's a triplet, right? So maybe it's better to call these two arguments triplet. So what I'll do is pluck out the original x, y, and z, of course, in that order. So that's my triplet. And now I need to basically iterate through all of the deltas, right? So for me, what I can do is maybe iterate through we'll say delta x. So delta x can be as low as -1. And we'll say go while delta x is less than or equal to +1. Notice that can also be 0, so I will eventually hit 0 here as well in the middle. And then I'll just keep incrementing delta x, right? So something like this. And I'll actually do that for all 3 of my dimensions. So it should be as simple as nesting these. This is my delta y, and of course my delta z. So that should be some good code. And then my neighbors would just be these coordinates that I get, right? So I can create my const, my single neighbor, by doing an array of x plus delta x, y plus delta y, and then z plus delta z. So that should give me all possible neighbors. And what I'll want to do is turn this into an actual node for me, which is a string. So I actually pass this into my get node from array syntax over here. Cool. And from there, I'll just go ahead and add that neighbor into some collection. Maybe I'll return it as another set. I don't see anything too bad with doing that. So I'll say const neighbors equals a new set. And then what I'll do is I'll I'll just add these, right? So neighbors dot add this single neighbor, right? Then after everything is done, just go ahead and return all of the neighbors. So let's go ahead and test this code. So let's say we called get neighbors on some position. We'll say the origin 0, 0, 0. And I know that I don't even have to check any bounds because they tell us that our like playable 3D area is infinite in all directions. So it's okay to have negative coordinates, right? So let me see what this looks like. It should be pretty long. So I have a little too much output over here. Let me comment out this original test for the initial nodes. We just want to look at that little test that we made, right? So this output, the set of size 27, comes from this. So here I recognize that there are 27 neighbors in this set, although there should be only 26. And that's because I included my original point itself, right? We're not going to consider a node itself its own neighbor, right? That would be weird. So for me, it should be as simple as after I generate all these neighbors, just remove myself. So neighbors dot, we'll say remove, or delete rather. I'll delete exactly my node. So a few ways I can do that. Maybe I'll just say triplet after I pass it into my get node, right? So let's see how that looks. So I should not have that 0, 0. That's looking much better. Cool. So these helper functions are definitely ones I feel like are going to make our main implementation a lot more reasonable. Now let's start actually coding up our main solution. So let's say that we had some function, we'll call it const. We'll say, I don't know, simulate. And we're going to take in some nodes. So I'll assume that this simulate really just goes through like one iteration of things. So maybe I'll call it step simulation. And it's going to take in some, we'll say, nodes, or the active nodes, and give us back the new active nodes. Maybe to be more specific here, I'll call this my active nodes. So if I wanted to just step through my simulation once, then it'd be me just calling step simulation exactly once, passing in my initial nodes, right? So that'll be our little test call over here. But in general, I know that active nodes is going to be some set. And what I want to do is create my new active nodes, right? So I'll say const new nodes is a new set. So let's start iterating through our existing active nodes. So we'll say for, we'll say let node of active nodes. And now I want to consider its neighbors. So let's say I got the neighbors of this node. It should be as simple as get neighbors of this node. Now that I kind of look at things, it looks like my get neighbors function, I defined it to take in the actual triplet and not the string. Here I actually wish it took in the string, right? So we'll kind of go with that. So I'll assume that this is some node, in which case when I invoke it, I'll just convert it into an array by splitting it, right? So maybe just simply node dot split on a comma, but be sure to actually map and turn it into a number, right? Because I need X, Y, and Z to be numbers for the arithmetic that I do later on. So that should be still compatible. Now I'm just assuming it takes in the string representation of my nodes. So I get the neighbors of that node. I'll call that const neighbors. And according to our rules in the problem, they say that, hey, if this active node has exactly 2 or 3 neighbors that are also active, then we're okay to keep it active. So I'll go ahead and just check, right? I want to check the count of neighbors here. So I'll say maybe let active neighbor count. So it starts at 0. I'm just going to check all of these neighbors. So I'll say for let neighbor of neighbors if that one is active. So if, let's say, the current active nodes has that neighbor, then it must be active, right? So I'll just go ahead and increment my active neighbor count. Active neighbor count plus equals 1. Cool. So this line specifically, or this for loop, gets the number of active neighbors that surround my node. And like they tell me in the prompt, if the active neighbor count, if it's 2 or if it's 3, then we can keep this as an active node. So it should be as simple as new nodes dot add this same node. And let's say that this if statement was not true, right? Let's say that it had, just one active neighbor, or it had 4 active neighbors. Then I would not add it to my new node list, which effectively makes it an inactive node in my next step of the simulation, right? Cool. So let's just go ahead and return new nodes. That should give us, I think, like mutation type 1 from our prompt, right? How do I manage nodes that are already active? And now here's the tricky part, right? And for our second type of mutation, when we have a node that is currently inactive, we only activate it if exactly 3 of its neighbors are active. So what I'll do to handle that is I'll create an object to really track the counts of the nodes that could be activated, right? So I'll create a function over here, or rather an object. I'll say const, we'll say to activate. Or maybe we'll just call this activation counts. Activation counts. Start as an empty object. And this object should only contain like nodes that are currently inactive, right? As the keys, and the values are how many active neighbors they have, right? So I think I'll want to modify this logic. So this refers to active neighbors, right? I know that this else would then refer to the inactive neighbors, right? So else this neighbor is inactive, so I'll add it to this activation counts. So quite simply, if we'll say this neighbor, if this neighbor is not in the activation counts as a key already, so I want to flip this Boolean. So if our neighbor is not yet within this object, then I'll just go ahead and initialize their count to be 0. So I should say activation counts of the neighbor should be equal to 0. And then in any case, if it's already there, I'll go ahead and increment its count. So say activation counts of neighbor should just be plus equals 1. Cool, so this gives me a way to track for the currently inactive nodes how many of their surrounding neighbors are in an active state. Nice. And now it should be the case that after my for loop, I have this completed activation counts. All of the nodes that are here inside of this object that have a number of exactly 3 in their value should be activated, right? So this is pretty straightforward. I can say for, we'll say let potential node, we'll say in activation counts. I'll want to check if the activation counts of that potential node is exactly 3, then go ahead and activate that one, right? By just adding it into my new nodes. By saying new nodes dot add the potential node. Cool, and that's giving back my new nodes. So let's test things. So let's say we step through just one call of our function. So maybe I'll give back some variable. We'll just call it, I don't know, state. So triplet is not defined. It's complaining about line 77 in get neighbors. So we'll go to that line. It should be over here. So not triplet. So instead, I'll just delete the plain old node, right? Because it's already a string. Because I made that little refactor from before. Let's try that now. Cool. So I have a lot of nodes here. That looks like some reasonable output. So in the actual prompt, the main thing now is to get a count of the active nodes after we run 6 iterations of this simulation. So I'll kind of clean things up over here. So I'll say let's state equal the initial nodes. So maybe I'll just say it like this. We'll say let state over here. And then I'll loop, about 6 times. So let I equal 0, and then loop while I, what's that? While I is less than 6, so that should give me 6 iterations. And what I'll do is I'll invoke step simulation on the state of the active nodes and then reassign that into my state. Cool. Then afterwards, I should just be able to return the number of active nodes, which would be the size of that collection, right? State.size. Cool, so let's see how we do over here. If this is working, we should get the answer, at least in part 1, of 298. So let's see this in action. Nice, and there we have part 1. Nothing much to this problem. So part 2 of this problem is actually very similar. All they do is ask us to add in a 4th dimension, which, depending on how you implemented part 1, could be easy or it could be a lot of extra work. For this particular solution, it tends to be a pretty quick refactor, right? So I already know the answer for my particular part 2 input. If this is working, I should get 1792 for the number of active nodes in like a 4D system. So I'll start by refactoring, this one, by adding in a 4th dimension. They call it W, so that'll be the 4th thing in my pair, right? So it goes X, Y, Z, W. And it's still the case that in your input, they're still giving you like just a slice, or a 2D slice. So you can assume that they lie in the same Z coordinate, 0 for me, and also in the same W coordinate, also 0 for me. So now I won't call this a triplet. I should call this a quad everywhere. And what else do I want to do? I want to fix this get neighbors now. So I have a W coordinate, and then of course I'll also need some delta W, right? So just nesting this even further, right? One loop for each dimension. So I'll call this delta W, and I'll also add that type of coordinate here, right? So comma W plus delta W. What I love about this problem is it really forces you to think in like an abstract way, right? As humans, we, pretty much have a really hard time visualizing 4D space, but we already know how to kind of generalize it for the 3D scenario, so it should follow accordingly for a 4-dimensional, spatial representation. So pretty neat problem the way they designed this. But now that I have get neighbors refactored and get active nodes, I think this might be already good to go. We shouldn't have to refactor our step simulation at all, right? Because we already have it generalized with just terms of get neighbors, right? Now it just happens that a node has more neighbors because it has other dimensions to be adjacent to. So really quick refactor. If I run that, I should be running part 2. There I have my 1792, and part 2 is no big deal at all, as long as we extended it properly. Awesome. So there's our walkthrough for day 17. This was a relatively simple problem, really just a problem that kind of asks us to stay organized in our code. That way we can extend it for the part 2. I'll catch you next time for day 18.